Significant digits dealing with numbers in chemistry. So basically learning about sig digs. Just a quick thing, exact versus measured values. If you have a counted number, for example, number of students of class, that would be a counted number. It's an exact number. It essentially has infinite number of significant digits. It is perfectly precise. However, any measured values, any numbers that result from a form of measurement, will be subject to some degree of uncertainty, depending on the precision of the measurements. So if you have a ruler that is graduated to millimeters, it'll be more precise than a ruler that's only graduated in centimeters or meters. So any measured values have a specific amount of significant digits that reflect the level of precision that the measurement was made with. As such, we need to understand what significant digits are so we can account for the precision of the measurements in our calculations. We may call these sig digs or sig figs for short, significant figures, significant digits, but basically they are numbers in a measurement that carry information. Digits that are significant in measurements include all non-zero digits, like 1, 2, 3, 4, 5, 6, 7, 8, up to 9. Any zeros between those non-zero digits are also going to be significant. For example, if you have a measurement like 2.05, this would have 3 significant digits in it. The 2, the 5, and since the zeros between them, it is definitely significant. Any leading zeros will not be significant. They're essentially placeholders giving you the scale of the number but not containing any information about the precision of the measurement. So for example, 0.006 would only have 1 significant digit. The leading zeros do not count. Trailing zeros are going to be significant. So for example, if you have a number 0.00503, the 5 counts, this 0 counts because it's between the 5 and the 3 counts, so this has 3 significant digits. The leading zeros do not count. They do not add any precision. If, however, you have 5, 0, 3, and another 0, so 0.005030, this would have 4 significant digits. The leading zeros don't count, the 5 does, the 3 does, the 0 between them does, and the trailing 0 does. It tells us some information. With the first example, we don't know what the next digit here is. So it has less precision than this example, which has a 0. We know what that 4th significant digit is. We have 2 of them, we know even more information. We now know that this is not 0.00503 something something. We know it's exactly 0.0050300, not like 4, 4 or 1, 2. We know for sure it is 0, 0. So this would have 5 significant zeros. 5 significant digits. Leading zeros don't count. Trailing zeros do count. One difference between chemistry and physics is that generally we don't have assumed values in chemistry. So when we have a trailing 0, we tend to count it as significant. In physics, looking at the number 150, they may just count the 1 and the 5 as significant because they'd be estimating the 0. We tend to be measuring all our values and including those. So in chemistry, we're going to count all trailing zeros as significant. To be sure, what you can do is you can put a decimal after the 0, and that would tell the reader for sure that we know that this is definitely a 0, not a 3 or a 1, and therefore it is significant. However, if you see a value in chemistry that just says 150, even if it's not written well, in chemistry, I'm going to ask you to count that as 3 significant zeros. 3 significant digits, the 0 as significant. Rounding. The 2 rules that you guys know for sure is that when you're going to be rounding a number off, perhaps because it has to be a certain number of significant digits, any numbers less than 5 that need to be rounded off, we just drop the digits. For example, if we had to round this number to 3 digits, because we are only allowed 3 digits of significance, the next number, the first one to be cut off is a 4, so we're going to be just eliminating those, and our answer would be 2.85, rounded to 3 significant digits. Don't round don't make the 9 round the 4, and then that happens like that. Don't cascade round. Just look at the next digit and decide if it's less than 5. We truncate it, and we get our answer. If the digit to be kept is followed by something that's greater than 5, we round up. So again, grade 4, you learned these rounding rules. If this one had to be rounded to 2 significant digits, again, leading zeros don't count, so we'd have to cut it off. We'd be looking at the 7, and we'd say that's higher than 5, so we're going to round that 8 up to 9. And there is our answer in 2 significant digits. However, when you have a 5, often people are taught that the rule with 5s are that you are supposed to be rounding it up. However, if you look at the number line, 1, 2, 3, 4, there's 5, 6, 7, 8, and 9. 5 is right in the middle. There's 4 numbers on either side of it. So if you were to constantly round 5 up to the higher side, what would happen is if you had a sample of a lot of numbers, you'd be biasing your sample size up higher than it should be. So what you really should do, since it's right in the middle, is that half the time it should be rounded up and half the time it should be rounded down. The way we do that is the rule that when you have a 5 to be rounded off, what you're going to do is you're going to round the preceding digit to even. So what that means is half the time it'll end up being rounded up, and half the time it'll end up being rounded down or left alone, because half the numbers that we'll be dealing with will be even and half of them will be odd. So for example, let's say we had 24.235 and we had to round it to 4 significant digits. We've got a 5 here that needs to be cut off. The question is, are we going to be rounding up or not? And so what we do is we look at the number that we're going to be rounding or not, and we say, okay, is it already even or is it odd? If it's odd, we are going to then round it up to even. So that would become 24.24. With this one, we have 18.125, and we've got to round it to 4 significant digits. So here, the 5, we consider, do we round that 2 up or not? And the rule says round the preceding digit to even. Since 2 is already even, we leave it alone, and the answer is 18.12. We're going to consider zeros as even, so if we have this rounded to 4 significant digits, the 5, we're considering rounding that 0, we're rounding it to even, because it is 5 that we need to cut off. It is just going to be 92.00. Consider 0 even. The rule is round even when dealing with 5s. Anything above 5, 6 is still going up. Anything below 5 is still going down. But when it's a 5, you're rounding the preceding digit to even. One example that would show how this would work is, let's say you had some money that you're borrowing from a friend. So $4.50 first day, $3.50 that you borrowed the next day, following day you borrowed $5.50, and then $2.50 the following day. When it came to pay them back, let's assume you could only pay them in loonies, so you decided to round each of these examples to the nearest dollar. And obviously these have been cherry-picked numbers to prove my point, but you can imagine if you had to calculate the total value, you've got your 4 measurements here, the actual value is $16 between the 4 days. If you, however, rounded 5s up every single time, you end up biasing the sample to a higher value than it really should be. If you round even each day, you're still doing the same amount of rounding, but you're switching the 5 rounding up sometimes and down sometimes, and therefore you're going to get a better value from the sum of the numbers. So bottom line is, if it's under 5, round down, over 5, round up, on 5, round to even. Calculations with significant digits, we're going to be doing mostly multiplying and dividing, and the rule for that is you look at the numbers that you're going into your calculation with, and whatever the number in your calculation that has the fewest significant digits, that's how many digits, significant digits, will be in your answer. So for example, if we were multiplying 2.0 centimeters by 1.56 centimeters, doing an area calculation, we can see the first measurement has 2 significant digits. Remember, trailing zeros count. The next one has 3 significant digits. So our answer, if you do it on your calculator, try it out, you get 3.12, but our answer can only be 3.1 because our least precise measured value only has 2 significant digits. So our answer can only have 2 significant digits. Our answer can't be more precise than any of the measured values gone into calculating. Adding and subtracting we're going to do very rarely, but when we do, the rule is you look at the decimal places. And so if you're adding numbers, you see how many decimal places you have in each of the measured values, and your answer will have whichever one has the fewest decimal places. That's how many decimal places your answer should have. Again, we're going to be focusing mostly on adding, multiplying and dividing at some point in our calculation. Quick note on scientific notation. Etiquette says that when you write a number in scientific notation, the first digit should be in front of the decimal, and then, depending on how many digits you had in your calculation, whatever else number you need comes after the decimal, and you multiply by 10 to whatever it is to get to the number that you want. So for example, if I had 1.0 times 10 to the positive 2, that would mean I have 1.0 that I'm multiplying by 10 twice. So I would have a value of 100. So this decimal place has been moved 1, 2 to the right. We've multiplied by 10 twice to get to the actual value. The problem is when you go to write it like this, it changes the number of significant digits. So often we will have to put our answers into scientific notation, because if I want to express the value as 100, the only way to do that in 2 significant digits would be by using scientific notation. So if we had a number like 183, we could write it as 1.83 times 10 to the negative 2. Either one of those both has 3 significant digits, but if we had to write in scientific notation, that's how it would be. Big number like this, if this was a measured value, all of those digits would be significant, and so if we were to write it in scientific notation, they'd have to show up with the same number of digits. 0.0047 will be written as 4.7 times 10 to the negative 3. We have a smaller number. It's going to have a negative exponent. It's as if we've divided 4.7 by 10 3 times to get us back to our real value of 0.0047. Make sure you can put scientific notation in on your calculator correctly, and you're going to do that by using the EXP button or EE button. Sometimes they have a times 10 button on your calculator, but make sure you're not actually pressing multiply by 10 and then hitting the exponent button. Use this. This replaces this part of your number. So instead of writing times 10, you're hitting EXP or EE, or depending on your calculator, the times 10. You are not putting in multiplied by 10. So try it on your calculator and make sure you can do it correctly. Just another example, 1,000 could be written as 1 times 10 to the positive 3. You had 0.001. Again, it's like having one that's been divided by 10 3 times. Alright, you should at this point pause the video and try out these 5 questions, making sure that you can write decimals as scientific notation and scientific notation as decimals, and get the number of significant digits correct. Here are the answers. So again, if you have a lot of precision in your measurement, and in chemistry we're going to assume all trailing zeros have been measured, they need to show up as significant in your answer as well. Leading zeros will not.